I am Vaibhav Srivastav from Vaibhav E-Learning Academy. Today we are going to continue our topic of Newton's laws of motion. This is our part number 5. In today's video we'll be learning about Newton's third law and we'll be learning about law of conservation of momentum and momentum. So in today's video we'll be discussing about Newton's third law. Then we'll be discussing about action and reaction. These two are the two types of forces. We'll be discussing about these two forces in detail. Then we have the proof, the derivation of the Newton's third law. We say that F1 is equals to minus of F2. How is that correct? We'll be deriving this in today's video. Then we will learn about applications of Newton's third law. In that a small topic is momentum. So then we'll learn about what is momentum. Then we'll be learning about conservation of momentum and we'll be doing a lot of numericals. So I hope you'll enjoy this video. Let us start the video with the first one, that is Newton's third law. Now what is Newton's third law? We all know from the starting that Newton's third law states that every action has an equal and opposite reaction. So this law is also called action-reaction law because it is based on two types of forces. The two forces are one action and the other one reaction. So this law states that if action is force F1, then the reaction will be force F2. Now action reaction does not mean that, for example, you punch a friend, then the friend punches you back. That is not action reaction. When you are punching him, then the action between your hand and his cheek, or the action between the cheek and your hand, that is known as the action and reaction force. So these are the two forces, action and reaction. This was the basic introduction about what was the Newton's third law. This law also states that F1 is equals to minus of F2. We will be deriving this in today's video later on, but this is the basic introduction about what is Newton's third law. Every action has an equal and opposite reaction. Newton's third law is fully theoretical. The main questions are from law of conservation of momentum and from the second law of motion. So this was about the introduction, what is Newton's third law. Now we will be discussing about action and reaction forces. So properties of action and reaction forces. Properties of action and reaction forces. So first property is they are equal in magnitude and opposite in direction. So equal in magnitude and opposite in direction. So this means that equal in magnitude. So F1 bar magnitude is equals to, they are equal in magnitude, it means that F2 bar. The magnitude is equal but the direction is opposite. So this is what the Newton's third law, first property of action and reaction forces is. Second property is they act on different bodies. So now consider a block of mass m kept on a table. Now the block m will exert a force on this table, or it will exert downwards, that is mg. The table will exert a force on the mass, that is normal. So our mg and normal action reaction pair. No, normal force and gravitational forces are not action reaction pair, because one point is they act on different bodies, but here when you are slapping a friend, then the action and reaction is happening between your hand and the cheek. It is not happening between hand and hand. So it means that different bodies. So mg and n, these are not action and reaction pair. If you consider there is an earth over here, the earth is pulling the block of mass m with the force mg. Now the block of mass m is also pulling earth with the force of mg. So mg and mg are action reaction pair. Similarly, this block of mass m is also exerting a normal force on the table. This normal force and the normal force exerted by the table on the block, those both forces are also action reaction pair. So one thing, that is, they act on different body. So here one body is the block, one body is the table. Another case, one body is the block, one body is the earth. So that is why we say that action and reaction forces are acting on different bodies. They are equal in magnitude, opposite in direction. mg is acting downward, this earth mg is acting upwards. Normal by the table is acting upward and the normal by the mass is acting downward. So these are the first two properties. Then they are the same forces. As we saw that normal and normal are the same forces. Gravitational force and gravitational force, both are same forces, but they are acting on different bodies and their magnitude is different. But magnitude is same, but the direction is different. They are the same forces and then they are internal forces. The normal and normal forces are internal in each other. You are not applying an external force on them. They develop, the forces develop between them, and then they, even gravitational forces are also developed between them. That is why these forces are known as internal forces. So the properties of action reaction force are, they are equal in magnitude, opposite in direction. They act on different bodies. They do not act on the same body. They are the same forces and they are the internal forces. These are the properties of action and reaction. Now this was about the properties. Now we know from all this, from the starting also, we know that F1 is equals to minus of F2. This one, they are equal in magnitude, opposite in direction. Now how do you prove this? For proving this, we have to understand the concepts of Newton's second law of motion. I have already said that first law and third law can be derived by using the second law. So I am going to derive the third law using the second law. So now we will be learning about the proof. Proof of third law. Now what is the proof of third law? So we know from second law that F external is equals to change in momentum by change in time, or change in momentum by time. Now if F net external is equals to 0, this is F net external. If net external force is 0, then delta P is equals to 0. If delta P is equals to 0, delta P means change in momentum. Change in momentum. If change in momentum is 0, it means that P final minus P initial is equals to 0. Now P final minus P initial is equals to 0. Now change in momentum is equals to 0. It means that momentum is conserved. Momentum is conserved. Now if momentum is conserved, it means that net momentum is equals to 0. Now conserved, there can be two cases. One case it is either conserved, one case it is 0. If it is 0, then also it is conserved. If it is conserved, then also it means that, it does not mean that it is 0, but conserved one case is that it is 0. If the momentum, net momentum is 0, it means that initially it was 0, finally also it is 0. So also it is known as conserved because the change is still 0. So net momentum is equals to 0. Net momentum is made up of P1 plus P2 plus so on is equals to 0. Now because we are talking about third law, we will be taking two forces, F1 and F2, or we will be taking two momentums, one of action, one of reaction. So we take 2. Now momentum is equals to mv, m1 v1 bar plus m2 v2 bar is equals to 0. Now what we have to do is differentiate with respect to time. So m1 dv1 by dt plus m2 dv2 by dt is equals to 0. Now what is dv by dt? dv by dt is acceleration. So m1a1 plus m2a2 is equals to 0. Mass into acceleration is equals to force. So F1 plus F2 is equals to 0. Thus F1 is equals to minus of F2. Hence proved. So this is the derivation of the third law of motion. So F net is equals to, from second law we say that F external, net external force is equals to change in momentum by time. Now if the net external force is 0, then the change in momentum is 0. If change in momentum is 0, then momentum is conserved. Momentum is conserved, it means that net momentum is equal to 0, or you can say it is conserved. So P1 plus P2 plus P3 infinitely is equal to 0, but here we are talking about two forces, action and reaction, so we are taking only two momentums. So m1 v1 plus m2 v2 is equals to 0. Now differentiate this with respect to time. If you are differentiating it with respect to time, mass comes out because mass is constant, dv by dt plus m2 dv2 by dt. dv by dt is acceleration, so m1 a1 plus m2 a2 is equals to 0. Mass into acceleration is equals to force, f1 plus f2 is equals to 0, and f1 is equals to minus of f2. This was the derivation of the third law of motion, of Newton's third law of motion. Now let us move on to the applications of Newton's third law of motion. The applications of Newton's third law of motion, it means that where do we use Newton's third law in everyday life. So application of third law. What is the application of third law? Because of action and reaction, we are able to walk. How are we able to walk? While we are walking, we are pushing the ground backwards and the ground is pushing us forward direction. So what we are doing is, we are pushing the ground backwards. We are applying a force F1. The ground is pushing us forward with the force F2. So it helps us in walking. Second, jump. When you are jumping, you are on the ground. You are applying force on the ground, F1. And the ground is applying force on you, F2, by the force you are jumping. Third is climbing a rope. While climbing a rope, when you are climbing it, what you are doing is you are pulling the rope down with the force of F1, and then the rope is pulling you up with the force of F2. Now this F1 is equals to minus of F2. You are applying force downwards and the rope is pulling you upwards, hence you are going up. So this is the third case. Now fourth case, walking, jumping, climbing a rope. Then the most important one comes is, swimming. Yeah, before that, swimming. Even during swimming, you push the water backwards and the water pushes you forward direction. So this is an application of third law of motion. So most of the cases in our everyday life are because of the third law of motion. Now the next most important one, second most important you can say, is weighing. Now it also helps us in measuring the weight. And the last one and the most important one is firing of a gun. These four examples are like everyday examples, but weight and firing of a gun are two different concepts. This firing of a gun is actually law of conservation of linear momentum. So we have to understand this for understanding the last example. And for weight, there is one concept. Now we all have heard about this machine known as weighing machine. We have heard about a weighing machine. Now, What is weighing machine? We say that weighing machine measures our weight. So for example, let us take this is as our weighing machine. Now this body has a mass m. He has a mass of m. So what we think is it measures the weight mg, but weighing machine does not measure mg, because but mostly in our problems what we do is if they give the mass of a body is equals to 5 kg, we assume that the weight is equals to 50 Newton, which is correct, but mostly if you see the concept that the weighing machine does not measure the mg, what it measures is it measures the normal reaction. The weighing machine measures the normal reaction. What normal reaction? See, the body is applying mg force on the ground towards the earth. Even one more thing, the body at the point of contact, it is applying a normal force. Because of this, the weighing machine is also applying a normal force on the body. Now this normal force, the normal force applied by the machine on the body is the reading. So when you are standing on the weighing machine, the point of contact between your feet and the machine is your feet is giving a normal reaction on the weighing machine, and the weighing machine is giving a normal reaction to your body. The normal reaction given by the weighing machine to your body is what we call it as weight. And why do we call it as mg? Because this normal reaction is equals to mg. If you draw the free body diagram of this body, then here mg and here n, and there is no acceleration, so we say that n is equals to mg. So that is why in problems we usually take it as, when they give the mass is equals to 5 kg, we take it as 15 Newton. But there is a concept of apparent weight which we will be discussing in the next Newton's laws of motion video in the pseudo force. In pseudo force we will be having a cases when this weighing machine is kept inside a lift and the lift moves up and down. Then there is a change in the weight. How that change happens? For example, this weighing machine is kept in the lift and the lift is going up. Then what happens is this downwards it is mg, up it is normal reaction, and the lift is going up with acceleration a. So n minus mg is equals to ma. N is equals to m into g plus a. And what does the weighing machine measure? Now here if you measure the mg, if you put mg that side, ma this side, then it will become wrong. You don't have to find the mg, you have to find normal reaction, because weighing machine calculates normal. Normal is equals to m into g plus a. Now n into g plus a, it means that when you are going up in a lift, then what happens is you feel weight gained. So that weight gain is due to this formula, m into g plus a. This concept we'll be discussing in detail in the next video, that is of pseudo force. So now this was all about weighing machine. Now comes the most important part of the video, that is momentum and conservation of momentum. But before moving on, there is one more real life application of Newton's laws of motion, that is hammering on the wall. So not on the wall, but if you take any block, if you take a wooden block, when you are hammering on the wooden block, we hold the wooden block. Why do we hold it? Because we are applying force on the nail on the block. The same thing, you are applying force on the hammer, hammer is applying the force on the nail is applying the force on the block. Block will also apply the force back on the nail, and nail will apply to the hammer onto you. Because if you are attacking the block should not attack you. What you do is, we take the other hand and you stop the blockage. So the force which the block has to give on you, it is delivered to your second hand. Thus the wooden nail goes inside. If you don't use your hand, then what happens is it slips. That is why the third law helps in this real life application also. So now let us move on to momentum and conservation of momentum. Let us see. So now we are moving on to the next part, that is momentum and conservation of momentum. Now first, before moving on, we have to understand what is momentum. Momentum is the quantity of motion of the body is called as momentum. Or in other words, you can say the ability of the body to keep the force is known as momentum. For example, you apply a force on the body, the ability of the body to maintain that force is known as momentum. This momentum is represented with P. It is a vector quantity. Momentum is equals to mass into velocity, and the direction of momentum is the direction of the velocity. Now, this momentum, we know about it now. What we have to learn important is the conservation of momentum, because that is where the questions come from. Now, conservation of momentum means that we are conserving the momentum. It means that the change in momentum is equal to 0. Again, from second law of motion, we know that F is equals to delta P by delta T. Now, if F external is 0, then delta P is equals to 0. Now, delta P is 0, it means that P final minus P initial is equals to 0. It means that P final is equals to P initial. This is called as conservation of momentum. This is the conservation of momentum. P final, you can take M final, V final is equals to this thing, you can take it as minus P final, P initial, M initial, V initial. So delta P is equals to 0, P final minus P initial is equals to 0. It means initial momentum is equals to final momentum. But this has one condition. The condition is that the system should be isolated. The system should be isolated. System should be isolated in the sense that there should be no external force acting on it. That when there is no external force acting, then only the initial momentum and final momentum will be 0. Now in the problems, what we have to do is, we have to take the initial momentum, they'll be giving that starts with rest. So initial momentum will be equal to 0. We have to equate 0 with the final momentum. So this is all about the law of conservation of momentum. Now about this conservation of momentum, we have some applications also. What are the applications? Let us see. Applications of linear momentum conservation. So first application is man jumping off a boat. So when a man jumps off a boat, what happens is, for example, this is the boat and this is the man. When he is jumping from the boat to the shore, he is jumping with a velocity v. The boat moves back with a velocity u, let us suppose. So this is also one law of conservation of momentum. Second one, when man walking on frictionless surface. When you are on a frictionless surface, it means that you cannot exert a force backwards. If you are not able to exert the force backwards, then you can't move forward. So in this case, what you have to do is, you have to either blow your air. For example, if this is the road which is without friction and this is the man, if he has to go that side, what he has to do is, he has to either sneeze this side or he has to blow air in the opposite direction. When he blows air, see what happens is, it creates some force. As we said that the system should be isolated. What is the system? Here the system is boat and the man. Here the system is boy and the surface. So in this, what it is happening is, as it is coughing or as it is blowing out air, it is generating an internal force. As we said that third law is actually internal force. So it is generating an internal force, and something is required to cancel this internal force. What is it doing? Because it is trying to make an internal force by blowing out the air, momentum is being developed. Because of that momentum, some velocity, he moves in forward direction with some velocity, and he does not move so far. It is because how much force he is exerting backwards, that much he is able to move. So the ability of the body to maintain the force is known as the momentum. he had applied some force on the opposite direction and he has moved in the opposite direction. Similarly, you can see in the jet skis. So what happens is, here if the boat has to move in this direction, the motor is applied here. What happens is, the motor blows the air this side and the the ship moves forward in the other direction. Now the third one and the most important is recoil of gun. Recoil of gun, when you fire a bullet from the gun, what happens is the bullet goes in forward direction, but the gun also comes in backward direction. Now this has one very good concept, that the bullet is moving with a larger speed, but why the gun is not moving backwards with a larger speed? It is because bullet has smaller mass, but bullet has large velocity, small mass, but the gun has larger mass and small velocity, and coincidentally both of them cancel each other. So that is why bullet moves with a faster velocity and less mass, and the gun it moves slowly but with a larger mass. So now let us learn about this recoil of gun, which is the most important concept, most important application of the conservation of linear momentum. Recoil of gun. So assuming this is as a gun and this is a bullet. Now when you are firing the gun, then what? When you are firing the bullet, we are applying the force on this, or when the gun is releasing the bullet, this bullet, let us assume that this bullet has a mass of small m, this gun has a mass of capital M. Now when you fire the bullet, the force is applied on the bullet. So this force on the bullet by the gun, and if you are taking the gun, then it is also moving backwards. Why? Because it is force applied on the gun by the bullet. So this is force applied on the bullet by the gun, and this is the force applied on the gun by the bullet. Now this mass of m moves with a velocity v, and then this gun moves backwards with a velocity of u. This is the concept of recoil of gun. So we are assuming that system is isolated. It means that F net external is equals to 0. What is this force on bullet by the gun, force on gun by the bullet? These are the internal forces. These, because see, the gun is trying to shoot out the bullet. How will it shoot? It requires some force. So it exerts some force on the bullet. This force, F on B by the G. Now force is developed. The equilibrium between the equilibrium in the isolated system is disturbed. Because the equilibrium is disturbed, what happens is the gun, even the bullet, applies some force on the gun. This is Newton's third law of motion. Every action has an equal and opposite reaction. So this is the action force, force on the bullet by the gun. This is the reaction force. Due to the reaction force, the gun moves backwards direction. So what happens is, because it is an isolated system, momentum is conserved. Okay. F net external is 0, delta P is equals to 0. P final minus P initial is equals to 0. It states that P initial is equals to P final. Because it is isolated system, initially it was 0. P final. Final momentum, what happened? One bullet, the bullet moves forward with mass m, velocity v. So m into v plus the gun also moves in backward direction, capital mass capital M, and velocity is minus u. What does minus represent? Minus represents the direction, because velocity is a vector quantity and vector quantity has direction. So we can say that mv minus mu is equal to 0. Thus we can say that mv is equals to mu. Now they will ask, what is the recoil of the gun? Then the recoil of the gun, u is equals to mass of the bullet into velocity of the bullet by mass of the gun. This is the recoil. This is the recoil of the gun. So this was the concept of recoil of gun in the law of conservation of momentum. Now in this, what model question they may ask? Let us take a small example. Let us suppose that this is the system. Let us suppose the mass of the bullet is 0.5 kg. 0. Or we can take 50 gram. The velocity of the bullet is 200 meter per second. It goes fast. Then they have given us the mass of the gun, capital M, or can take mg, this mb, vb. Mass of the gun, for example, it is 20 kg. We have to find the velocity of the recoil. So what we have to do is, we should see that first we should assume that it is in an isolated. You have to see, is there any external force? There is no external force inside. All the forces are internal, that is bullet and the gun. So what we do is, F net is equals to 0, dp is 0. So momentum is conserved. It means that initial momentum is equals to final momentum. What is initial momentum? 0. What is final momentum? Velocity. Final momentum is mass of the bullet into velocity of the bullet plus mass of the gun into velocity of the gun. What is mass of the bullet? It is 50 gram. So 0.05 kg into velocity is 200 plus mass of the gun is 20 into velocity is u, for example. Now 0 is equal to this value. Now cancel this. 5 2s are 10. So 0 is equals to 10 plus 20u. This 10 goes this side, minus 10 is equals to 20u. Minus 1 by 2 is equals to u. U is equals to 0.5 meter per second. So here in problems, you don't need to assume that one is going in forward direction, one is going in backward direction. See here, I could have taken velocity of gun to be minus u, because we know that the gun will move backward. But in most of the problems, we don't know which is going forward and which is going backward. Then you can assume one, or you can either keep the value as u. If it is going backward, the reaction will balance itself. The reaction has balanced itself and u we got negative value. It means that the gun is moving backwards. So what we did is, we assumed this is moving in forward direction. We did not take anything as negative. The reaction balanced itself and it made that the velocity of the gun is in negative. So this was all about the recoil of the gun. Now let us move on to the next topic of this video, that is about numerical. We'll be discussing many numericals, some 3 or 4 numericals. So let us see. So now we have our first question over here. A man of mass 60 kg running along the rails with a velocity 6 meter per second jumps into a car of mass 90 kg standing on a rail and stops there. Find the velocity with which the car will start moving on the rail. So here they did not give any external force. So we are saying that F net external is equals to 0. So we are saying momentum is conserved. So delta P equal to 0. P final minus P initial is equals to 0. So what we are saying is, initial momentum is equals to final momentum. Now what is the story initially? Initially is running along the rails with a velocity 6 meter per second. Initially we are not taking 0 because they have written running along the rails. So mass is 60 kg. 60 into running around the rails with the velocity 6 meter per second. 6 is equals to final momentum and stops there. So finally he stops there. Find the velocity with which the car will start moving on the rail. Now what happens is, he is jumping onto a car of mass 90 kg. Now initially the man is moving with 60 kg man is moving with 6 meter per second, and the 90 kg car is at rest. Initially it is at rest. So it is the what is it? It is V1. It is U1. It means that the man was moving with 6 meter per second, but the car was at rest. So that is why we take it as 0. Final momentum stops there. So man stops there. So man is equals to 60 into 0. This is V2 plus. Find the velocity with which the car will start moving. Now mass of the car. What is the mass of the car? 90 kg. No, this time the mass will be 90 plus 60 into velocity. Why 90 plus 60? Because this time the man is also on the car. So 90 plus 60 into velocity v. Now what you have to do is, you have to just multiply. 360 is equals to 150 v. Velocity is equals to 360 by 150. That is equals to 12 by 5. That is equals to 2.4 meter per second square. Here it is not a negative. It means that what is happening in the situation is, for example, this is the car on the rail. The man is running. We are assuming the man running direction is equal to positive direction. Imagine the man is running like this with 6 meter per second. Assume that is the positive direction. He is jumping on the car. The car will also start moving in the positive direction. He is jumping on this. It won't move back. It will move in the forward direction. That is why the answer is in positive. This was our first question. What we did was, initial momentum is equal to final momentum. Let us move on to two more questions. Let us see. So now we are on the next question, that is, a hunter has a machine gun that can fire 50-gram bullets with a velocity of 900 meter per second. A 40 kg tiger springs on him with a velocity 10 meter per second. How many bullets must the hunter fire into the tiger in order to stop the attack? So here also we are considering the net external force is equals to 0. So initial momentum is equals to final momentum. Now initially what is happening is, a 40 kg tiger is jumping on him. It is jumped on it. The tiger is jumping on the hunter. So what is the mass? Mass is 40 kg with a velocity of 10 meter per second. This is the initial. It has 50-gram bullets with a velocity of 900 meter per second, but initially it is at rest, so it is 0. So to stop this, what it has to do? The hunter must fire some bullets. So what final momentum it will become? So initially let us take mass of the tiger into velocity of the tiger is equals to mass of the bullet into velocity of bullet into n. Why n? Because we don't need one bullet to stop it. We need n number of bullets to stop the tiger. So we have to find the n. So mass of the tiger is 40 into velocity is 10 is equals to mass of the bullet is 0.05 into velocity is 900 into n. Now n is equals to 400 by this point and these two 0, 45. N is equals to for this 40 kg tiger springs on him with the velocity 10. So 400 is equals to mass of the bullet is 50. So 0.05 kg into 900. 0.05 into 900 for 450. This will be 450 by 45. So n is equals to 10 bullets. So what we did is, initial momentum is equals to final momentum. Initially mass of the tiger, initially it is jumping, the 40 kg tiger jumps with the velocity of 10 meter per second. So to stop that, n into m into v we have to find n number of bullets. So mass of the bullet is 50 gram, that is equals to 0.05 kg. 0.05 into the velocity of the bullet is 900. So 900, so 9 5s are 45. Now this is actually 400 only, right? 400 by 45, sorry. So almost this value will be equal to 9 bullets. Yeah. So this is 400. This 9 5s are 45 comes downwards. So n is equals to 400 by 45. So 9 bullets. So the hunter has to fire 9 bullets in order to stop the tiger's attack. This was the second question. Every question we have to use the conservation of momentum. Now this was the second question. Now let us move on to the next question. Let us see. So now we have our last question. A spacecraft of mass 2000 kg moving with a velocity 600 meter per second suddenly explodes into two pieces. One piece of mass 500 kg and is left stationary. The velocity of the other part must be. So here one spacecraft, initially we are taking initial momentum is equals to final momentum. Initially the spacecraft of mass 2000 kg. So 2000 into moving with the velocity of 600 meter per second is equals to Now finally what is happening is one piece is breaking into mass 500 kg. So 500 and is left stationary into 0 plus the other piece. Now one is of mass 2000 kg and one part is of 500 kg. Other part is of 1500 kg into. We have to find the velocity of the other part. So v. Now this value is equals to, this value will become 0 and 1500 into v. This 0 gets cancelled. Velocity is equals to 1200 by 15, which is equals to 800 meter per second. So what we did here is initial momentum is equals to final momentum. Initially the spacecraft was 2000 kg. This becomes into two parts. One becomes 500 kg and other becomes 1500 kg. Now this 500 kg is stationary. This part is stationary. The second part moves with some velocity v. This velocity we have to find. There is no external force, so we are taking that the momentum is conserved. Initial momentum is equals to final momentum. Initially it is moving with 600 meter per second. So 2000 into 600, this value. And finally one piece is at rest, so it is 0, and the second piece it has 1500 into v. We have to find the v. We cancel out the zeros. 12,000 by 15 is equals to v, and velocity is equals to 800 meter per second. Now this is the basic concept of linear momentum conservation. In more detail we'll be learning about center of mass. So I hope you have enjoyed this video. In today's video we learned about Newton's third law and linear momentum. So see you next time in the next video. Like, share and subscribe. Thank you.